Okay, so we are currently studying about this parametric vector form, and last time we mainly talked about something called a homogeneous linear system, right? So we simply change, or we simply set the b vector as all 0, right? And then how we solve it is exactly the same. So we change it to a reduced echelon form, right? And then see. So given this type of a solution, we further change it to a vector form. So that's why we call that as a parametric vector form. And then that vector is represented as this kind of a solution vector that contains all of our variables. And then this vector can be represented as some kind of constant vector which specifies some particular direction, right? So all these numbers are obtained as a constant, and then we have those kind of free parameter that can freely stretch out or shrink the length of this vector, right? And then in case we have two free variables, and then each of our free variable will work as, or we will play a role of this kind of free parameter in this parametric vector form. And then for each free variable, we have a particular constant vector that specifies each of two directions. Okay, and then our solution now can be represented as basically a linear combination of these two constant vectors, right? And then the solution set for this homogeneous linear system can be viewed as this kind of span of these two vectors, right? And so our solution vector containing all the variables will be forming some kind of a hyperplane, or this kind of plane stretched by these two vectors. And then we now discuss about this non-homogeneous linear system where we have this kind of non-zero vector. Okay, but here we are assuming we still have the same exact. See. One second. Yeah, again it's me. Sorry. Okay. Okay, so the dimension of the span, or the number of vectors that we use to form our span, will be, the number of vectors that we will have there will be exactly the same as the number of free variables that we have, because each free variable will generate one of these vectors. Okay, and then yeah, so we talk about this non-homogeneous version of the equation, and then yeah, as we can see, when changing it to a reduced echelon form, and then this coefficient part will exactly the same, and thus, yeah, so if you compare this part and also this part will exactly be the same, right? And so the only different part will be this part. So in the case of an homogeneous system, this will remain always the same, always as a zero vector. But in non-homogeneous case, for example, this part was something like 7 minus 1 and minus 4, and then this value will change to some non-zero vectors, and then these part will remain the same because this part is the same, and we have the only different part for this. Okay, and so when changing this guy into a kind of standard form where we have a basic variables on the left and the remaining part, including a free variable on the right, and then we have this kind of solution. And then we still do the same thing of this parametric vector form. So we have this kind of constant vector that came from here, okay, and then the remaining part can be factorized into the exact same form of a parametric vector form from the homogeneous linear system case. Okay, so in general, the solution for non-homogeneous linear system can be represented as this from the previous example. So we have this kind of vector that specifies some direction as a constant, and then we have this kind of free parameter over x3, which is represented as t in this form, and then we have some constant vector p. Okay, and then let's think about the geometric interpretation or geometric shape of x3 times this. So this was our solution for a homogeneous linear system, but in the case of non-homogeneous linear system, the first part is the same, and then we have this kind of constant vector, minus 1 to 0, and then this guy, you guys know, in this three-dimensional space, we have some direction determined by this vector, something like this. And then by changing the length of this vector x3, we have this kind of solution, right? And then let's think about the points along this, the points from this representation. In this case, still we have this kind of direction. Exactly the same as this red vector, but instead of starting from 0 or origin, we start from this vector So this vector, suppose x1, x2, x3, and then this kind of solution is here we have -1 and 2, and along the x3 we have 0. So the new point will be somewhere here, and then we are moving this origin to this new point, which is non-zero point. And then this vector will be moved to a non-origin, right? So it's still kind of a line. It's still a line that has exactly the same direction, okay? But it's a moved version, okay? Because it's no longer crossing a 0 or origin. It's crossing some kind of non-zero point, and that point is specified this. Okay, so that is a main point in this chapter. So homogeneous, the solution for homogeneous version and non-homogeneous version, they are having kind of same directions as their solution set, but only they are kind of translate or moved version in parallel. And moving in parallel is called translation in mathematical term. Okay, in mathematics, translation means parallel movement between some point or lines or some kind of polygon and so on. Right. So translation means parallel moving to some other position. Okay. Okay. Then what about the other case where we had a two free variable? In that case, the original homogeneous linear system had a kind of solution as a kind of plane. So suppose we have these two vectors associated with each of our free variable, and then suppose the solution set for homogeneous linear system will be this kind of hyperplane or this kind of plane, right? And then let's imagine it's a non-homogeneous version, which will have a kind of non-zero vector in this place. And then instead of starting from origin, it will start from some non-zero point. But still, this plane will be moved in parallel, right? So still, it can be viewed as a kind of translated version of the same plane. Okay, and then this relationship can be also understood from what we learned in high school or middle school. So as we saw, this part is specifying some kind of direction, right? And then one really simple case of a linear system is this kind of linear equation. So I'm gonna give you this kind of information and ask you to obtain the equation for the line. So I'm gonna give you information of slope is 3, and then one point crossing this line is just 0, 0. And then what is the equation for our line? It's y equals 3x, right? Yeah. And this is exactly one case of a homogeneous linear system, because so let's change it to x1 and x2, and then 3x1 minus x2 equals 0, right? Okay, and then now let me ask another question of having a slope of 3, and then this line crosses, or this line goes through some point of 1, 2. In that case, how do we formulate our slope? I mean, our equation for the line. And then we are kind of changing it as this: y minus 2 equals 3, x minus 1, right? And then still 3x minus 3. Then this guy will be moved to here, right? Something like this, right? So still we have the exact same slope, which means we have the same direction, okay? And then let's think about the solution for the parametric vector form for here. So what is a matrix form or augmented matrix for this equation? It will be 3, 1, 0, right? And then is this echelon form? Is this echelon form? Yes or no? Yeah, it is echelon form, although we have just a one single row, so we find this yeah. Right, thanks. So 3 will be our pivot, which is our first non-zero entry in the first row, and then we look in the bottom and there is no more entries, so we are still happy. And then so this is echelon form. Then in order to have a reduced echelon form, it will be it will be scaled by this, right? And then x1 equals x2, right? And then what is our parametric vector form? x1, x2 equals what? x1, yeah, so it should be something like this, right? And then the first one is x2, so it should be like this. And then what about the second part? x1, right? And then we of course have a zero vector, right? So it is kind of saying as it is kind of the same as our slope that we are initially given, which specifies the direction of our line. So this specifies direction, and then this is a 1 point crossing this line, and this is an origin in this case, okay? In this case, for the solutions for this requirement, I mean satisfying this requirement will be something like this. And then can you tell me what the value will be here? So instead of passing through the origin, we are passing now 1, 2. So it will be something like this, right? Right? It's conceptually the same. I mean, we know how to obtain the equation for the line from these conditions or these information, right? And then the meaning of it is we have this we have the same direction, but we have one single point that our line passed through. Okay, and then oops. And then from this analogy, like this, and then what about, so let's see. So slope is still 3, and then the point that this line goes through is 1, 2. So 1, 2, something like this. And then we know y minus 2 equals 3x minus 1 and 3x minus 1, right? It surely satisfies 1, 2. I mean, when plugging 1 and 2 in x and y, it will be true. But what about this? So what if we give like x as 2 and then y as 5? So I'm going to change this problem as having still the same slope, but the 1 point of this line is 5, 2. In this case, the resulting line, the equation for the line, is still the same as this, right? So from these two examples, we know that in order to represent the same line, just like this, other than our slope, we can give any of these 1 point of this line, right? It can be 1, 2, but it can be 5, let's see. It is not 5, 2, it is 2, 5, right? Then, yeah, so in this example, so we can give just only 1 point that is in our line, but it doesn't need to be unique, right? So it can be any of the point in this line, okay? So again, if we are given just a slope, which specifies the direction, and just any 1 point following our line or some kind of plane, yeah, it will be just enough. I mean, the resulting plane or resulting line can still be the same. Okay, so this last theorem is saying about this kind of characteristic. So let's read through them. So we are given this non-homogeneous linear system, and then then we think about this homogeneous linear system, and then we first obtain the solution. I mean, basically all the solution for this. Okay, just like a parametric vector form. And then we just supply, or we give just 1 point P, which is on this equation. Just 1 point. Okay, it can be any point that satisfies this, and then it's working just like this kind of point, 1, 2 or 2, 5. Okay, so it can be any point. And then you give this point, and then you combine it, or basically you add it with the solution from this homogeneous version of the linear system. In that case, that solution will be your answer for this original non-homogeneous version of the solution. Okay. Okay, then okay, so we learned about the meaning of this translation. So I already explained it. And then in this case, where we have the direction vector and some constant vector, okay, in that case it's also called the equation of the line that pass through some point P parallel to V. Okay, so in this case P plus some kind of scalar times V. So this line is called the equation of the line through P, which means this line passes through P, and this line is parallel to this vector V, or V is specifying the direction, and P is giving just 1 point of this line. Okay, so geometrically it's like moving this line in parallel, so that this origin becomes some non-origin point. So yeah, I think that's it for chapter 1.5. Questions? So in practice, yeah, so as you guys might know, the homework, the new homework was posted. Okay, and then when solving some exercises in this chapter, I mean, yeah, even though you have understood this kind of theorems, but what you will actually do when solving for some exercises in this chapter will still be the same. So you basically do this kind of a row reduction to obtain reduced echelon form, and then do this kind of parametric vector form. Okay, so that's probably it. But you have to understand the meaning of it. So those vectors associated with our free parameter that will specify the direction. Okay, and then the other constant vector came from our B vector. So that is giving just a 1 point of our solution set, or yeah, whether it's a line or plane, and so on. And of course, if we have a three free variables, not just two. So suppose we have three free variable, and then we are having three different vectors, and then the span of these three vectors will be what? Like a three-dimensional shape, right? But this three-dimensional kind of space might be in like a four-dimensional space or five-dimensional space, and so on, right? So geometrically, and this is a really important part, and this will appear again in maybe 1 or 2 weeks later. So suppose we have five variables, and then our parametric vector form will be something like this: x1, x2, x3, x4, x5. Yeah, that's obvious, right? And then suppose we have like three different free parameter, which means from some of our augmented matrix. So suppose we have a B part here, and then this part will have like a three non-pivot column. So which means we have only two pivots, okay, and three non-pivot, which does our free variable. And then suppose that free variable was x2, x4, x5, and then x2 times this, x4 times this, x5 times this, right? So basically the solution will be the span of these three vectors, right? Then what is the original dimension where these three vectors are living in? It's five-dimensional space, of course, because we have five variables, right? So in five-dimensional space, although it's difficult to imagine, but in this five-dimensional space, this kind of three-dimensional kind of subspace, okay? That subspace can be thought of as kind of a plane, right? So very thin plane in our three-dimensional space, right? And then here, in this case, it's a little bit subtle question or kind of tricky question, but let's think about this case. So even though we have these three vectors, what if these three vectors are actually living in two-dimensional space? So we already saw some example where I'm going to give you just one vector, and span of it is just line, and then I'm going to give you the second vector, and then the span will be plane. And I will give you the third vector, and third vector is not, if that third vector is not inside of this plane, and then it will actually increase our span, right? But what if this vector, third vector, is something like this, where this vector is exactly inside of these planes spanned by these previous two. Okay? In that case, even though we are given three vectors, the span of all these three will just remain as this 2D space, 2D space or 2D plane, right? So in this case, it seems like we cannot guarantee that the solution space or the span of these three may be actually like just plane instead of a three-dimensional kind of volumic space, volumetric space, right? But in this case, those vectors are all, so if you think about adding one vector at a time, just like these cases, first and the second and the third and so on, okay, the vector that we will add will not be inside of the span of the previous vector. So it's always true in this specific case. Okay, I mean in this specific case, I mean those three vectors are coming from changing our solution into parametric vector form. Okay, in that case, those three vectors are always it will give, or it will always increase our space. Okay. So I will come back to this point, to describe why it should be true. Okay, it will be after studying the next chapter. Okay. Questions? 네, 맞아요. So the question, let me repeat the question of a student. So if we have a maybe three free variable, and then we guarantee that our solution set will be three-dimensional space, not just a two-dimensional plane or one-dimensional line, right? Okay, then the next chapter is 1.7, which is about the linear independence. And we skip 1.6 because it's just describing one particular application. And then 1.7 is about this linear independence. Linear independence is the case I just described. So we have two vectors, and then the third vector is not inside of the plane of the previous two. Okay? In this case, we call that as linearly independent. I'm just giving you kind of high-level understanding about what that means. And then if third vector is inside of this plane of the previous two, then they are linearly dependent. Okay? Okay, so let's look into the definition of this linear independence, and it's nicely extending our homogeneous linear system. So we still talk about the homogeneous linear system, AX equals 0, and then in this matrix equation form, we can think about its vector equation form. So suppose we have 1, 2, 3, 2, 3, 4, and 0, 1, 2. And our x is x1, x2, x3 equals 0, right? And then in this case, this can be represented as 1, 2, 3, and 2, 3, 4, and 0, 1, 2, and then their linear combination with x1, x2, x3, right, equals 0, right? And so it's some linear combination of these three vectors with those linear combination coefficient or weights, right? Okay, so this vector equation or matrix equation has the same meaning. And in terms of this linearly independent, I mean the meaning of this linear independence means those three vectors are linearly independent, and the definition for it is when, yeah, they are linearly independent when this homogeneous linear system has the solution of only just zero vector. Okay, which means this homogeneous linear system, whether it's a matrix form or a vector form, if the solution is only just one and all zero vector, okay, if we have only one solution for zero vector, and then in that case those three vectors are linearly independent. So that is the exact definition for linear independence. And what about linear dependence, or when they are linearly dependent? It's the opposite case. For our homogeneous linear system, if the solution is more than one, okay, more than just all zero solution, I mean, if we can find some other solutions, and then that's when we call those three vectors are linearly dependent. Okay, so that is the definition. Okay, so that additional solution, I mean, by default, we already learned that this homogeneous linear system will always have a solution of all zero vector, and that solution is called what? What was the name for that solution of all zeros? Homogeneous linear. Yeah, we talk about the homogeneous linear system, and we know the homogeneous linear system has the solution of all zero vectors all the time. I mean, yeah, we still think about 0b case, and in terms of the solution for x. So here, if we plug all zero into these linear combination coefficient, yeah, we always know that. I mean, we know that it's always true. So this particular solution of all zeros is called trivial solution because it's trivially obtained. It's very, very easy to obtain this solution. And the situation where we have more than this solution, if we have other solution than this all zero solution, and that solution will be, we'll have some non-zero value somewhere in x1, x2, and x3, right? I mean, if we have other solution than this all zero vector, and then that solution will have some non-zero values somewhere in x1, x2, and x3, right? And those are called a non-homogeneous solution. And then it means in this case of a vector equation, the linear combination weights are not all zero, so some are non-zero, right? And using those non-zero weights, we can still make this equation true. So that's the meaning of a linear dependence. Okay, then yeah, let's look at the example. So we are given these three vectors, v1, v2, v3, and then we have to determine if these sets, this set of these three vectors are linearly independent. Okay. Okay, and so we construct this homogeneous linear system, and then still what we have to do is to change it to this echelon form. Okay, and then whether we have only one solution for this trivial solution, or whether we have more than one solution, was determined by whether we have free variable or not, right? So in this case, we have a pivot here and here, and then the third variable x3 doesn't have a pivot, and thus it's our free variable, and this free variable will give some non-zero solution, right? Yeah, so that non-zero solution, I mean, just to help you understand, let's see. Yeah, let's look at this simple case where we have a one free variable of an x3, and then it will give this vector, right? It's still the same thing that we saw, and then by freely choosing x3 as some value, for example, x3 was 1, and then that weight will be exactly like this. So if we plug in these three values into our equation, and then we still make the equation be true, right? So those are working as a non-zero weight value. Okay. So since we have a free variable, this homogeneous equation will have infinitely many solutions, not just only one solution of all zero, right? And so this is the case where those three vectors are linearly independent. Linearly dependent. Okay, so they are linearly dependent, and then this exact case is the same as like this case. So we have two, and then the third one is inside of the span of the previous two. Okay, we will see why in more detail. Okay, and then here in this example, we are asked another question. So the second question is, if they are, if it is possible, or if they are linearly dependent, and give me that exact linear dependence relation, okay, among these vectors. Okay, so again, the definition for this linearly dependent means for this homogeneous linear system, we have to find out some non-zero values for these C1 through Cp. Okay, and what is those values? So that is the question asked here. Okay, so that example or that solution is still found by our parametric vector form. So we obtain this, and then let's see here. What will be our parametric vector form? So here we know we have a free variable on x3. And then what is the value here? What is the first value? It's 2. And what about the second value? -1. And what about the third one? It's 1, right? It's 1 because x3 equals x3. That's where we obtain this 1. Okay, and then x3 again is a free parameter, and then let's just simply choose just 1 as our free parameter, and then 2 minus 1 and 1 is the solution for our vector equation, right? And then in this case we chose x3 as 5, then the corresponding solution for this linear combination weight will be 10 minus 5 and 5 equals 0, right? So this is a linearly dependent relationship, and this is the answer for this question. Find a linear dependence relation. Okay, then Okay, so in this example, let me explain why this is corresponding to the case where we have this exact case. Okay, so suppose we are given v1 and v2, and they are something like this. And then the third vector, again, I mentioned that this guy is inside of the plane of these two, right? And what's the meaning of it? The meaning of it is the third vector can be represented as some linear combination of these two, right? So that's why this guy is inside, or this guy was contained or included in the span of these two. The definition of the span is what? All the possible linear combination of these two, right? And the fact that this guy is inside of the span means those two vectors can represent, using their linear combination for, these two vectors can represent this vector as their linear combinations, right? And that linear, let me ask you, what is that linear combination representation of V3 is some linear combination of V1 and V2. What is that? So more exactly, some value and V1 and some value plus V2. And these are, of course, vector. Okay. What will be these two values? You can easily obtain that value from here. So we move these, this guy into the right hand side and then divide it by 5. And then this value will be 2, comma, what? What is this value? So, I'm doing this. V3 equals 2V1 minus V2, right? So, this guy is minus 1. So, we are having minus 2 and 1 as a linear combination weight that represents this third vector, right? And what about the linearly independent case? In the case of linear independence, the solution for this equation will always be 0 times V1 plus 0 times V2 and 0 times V3 equals 0, right? So this is only that is only one possible representation for this homogeneous linear system, right? So it means, so from here, let's try to represent V3 equals some V1 and V2. It is not possible because V3, the coefficient is a 0 here, right? So that should be some non-zero value, and that's when we can change it into this form, right? Okay, and then let's look at some special case. So I'm going to give you 3 vectors, V1 and V2 and V3, and then still the question is to determine whether they are linearly independent or not. And then suppose one of these 3 vectors are 0 vector. So V2 is all 0, which is basically just an origin, the vector of an origin. Okay? So in that case, the question is whether they are linearly independent or dependent. That is linearly dependent. And why? And so by definition, they are linearly dependent. Okay, so yeah, let's understand why. So by the definition of linear independence, those three values should be some non-zero value. I mean, yeah, some non-zero value, which means at least one of them is non-zero, and then that will be non-zero solution, right? So I'm going to give you one really easy solution satisfying this. So since v2 is zero vector, so we set 1 here, and then 0 and 0. So basically our solution is 0, 1, 0. In that case, what is the resulting vector? It's still 0, because we multiply v1 and v3 as 0, and we multiply v2 as some non-zero, but the v2 itself is a 0 vector, so the result is a 0 vector, right? So that is a easily obtained solution for kind of non-trivial solution. Easily obtained non-trivial solution, right? So by setting that way, by setting our solution that way, we can easily find some non-trivial solution, and thus those three vectors of v1, v2, and v3 are linearly independent. Linearly dependent. Okay, and let's try to understand this situation by using my fingers still. So suppose we are given v1 and v3, and then the last vector, which is v2 now, is exactly 0. Okay, 0 vector, which is our origin. And the question is whether this 0 vector, which is our v2 here, is v2 inside of the span of these two. So 0 is, of course, inside of a span of any vector, right? So it's already inside of the span of these two. Okay, and also if we imagine the span of these three, we have 2, and then we have a 0 vector, right? This 0 vector doesn't increase our space of our span, right? Sure. Okay, so from here, we can understand that in your vector set, if you are given a set of vector, if at least one vector is exactly 0 vector, and then you can immediately obtain the answer that they are linearly dependent. Okay, and then let's think about another special case where we have only 2 vectors. Okay, so previously we talked about like the case where we have a 3 vector. So we are given 2 vectors initially, and then we talk about the cases, different cases in terms of these third vector. But we are only given just a 2 vector, and then we start with the 1 vector, and that vector should not be 0 vector. Okay, because if we see 0 vector in our vector set, and then we can automatically say that they are linearly dependent, right? So suppose this vector is not 0 vector, and it has some direction. Okay, and then the question is what kind of a vector for this second vector will make our vector set of these 2 as a linearly dependent. I mean, when the 2 vectors are linearly dependent or independent. So that's the question here. So I'm going to give you 1 vector first. And then if the second vector is outside of the span of the first vector, something like this, and then they are linearly independent in between these 2. But when are they linearly dependent? So the second vector should be inside of the span of the first one. And then what is the span of the first vector? It's just a single line, right? And then the second vector should be something like this, right? Which means the second vector is just a scalar multiple of the first vector, right? Or it can be like other direction, but my finger cannot stretch with the 100 degrees, right? Okay, so that means if they are linearly dependent, then one vector is always represented as a multiple or scalar multiple of the other vector, right? It's basically along the line, along the same line, expanded by the first vector. Okay. Okay, and then let's learn this theorem 7, linearly dependent sets. Okay, so this theorem, it's not new. It's exactly following our intuition of adding one vector at a time. And from the original definition of a linearly independent or dependent sets, suppose we are given these vector sets, then what was the definition? Original definition of a linearly independent sets. So we have V1, V2, and V3 equals 0. So we still think about this homogeneous linear system, and then if at least one of them is non-zero, and then that's when they are linearly dependent, and that solution is a non-trivial solution for this homogeneous linear system, right? And then it means, so here, suppose at least one non-zero entry was found, something like here. So at least we are assuming this guy was maybe 3, okay, which is some non-zero value, okay. So this is the original definition for linear dependence, right? And it means this case is this case can be described as a slightly different version. So in this case, some vector is represented as linear combination of the others. So in this case, this guy is V3, this guy is V2, and then this part will become the linear combination of V1 and V3. Okay, so those two equations are saying the same thing. Okay, so they are just they have just a slight difference, very small differences. Okay, so again, the first version is among those linear combination coefficients, at least one should be non-zero, right? Because if they are all zero, and then it's our trivial solution, right? And if at least one of them is non-zero, and then that's when they are linearly dependent. And then in that case, suppose that non-zero coefficient was found in V2, and then regardless of what those values are, we can just move this term into the right, and then divide each side of this equation by 3, and then we will obtain V2, right, as some linear combination of V1 and V3. Okay. Okay, so this theorem is saying that these two cases are the same, okay, which is quite easy to understand. So they are linearly dependent, right? So by definition, we should be able to find some non-zero vector here, and then that is the same as at least one of the vectors can be represented as a linear combination of the other. So those two things are equivalent. So those equivalents are described by this, the meaning of this theorem 7. Okay, and then additional statement here saying if S is a linearly dependent, then some Vj is a linear combination of using previous vectors. So suppose we have V1 through V100. So we are given 100 vectors. So there are so many. So if you imagine like doing all the row reduction on this 100 vector matrix, it will be terrible. It will take a lot of time, right? But one fortunate fact that we can utilize is that if we can find some linear combination, okay, so yeah, let me explain it in this way. So we are given 100 different vector, okay, and then the question is still to determine whether they are linearly independent or dependent, okay, and then we start with the only one vector, okay. Although we have 100 vector, we only consider just the first vector, and then what is the case when the first vector is linearly dependent? So we are given just one vector, and then when is this vector linearly dependent? So we are given only one vector, and then let's form the homogeneous linear system, right, by setting it as 0, and then still the same definition applies. So here, regardless of what this vector is, if we plug this value as 0, it will be true all the time. But when can we place, or when can we plug this value as non-zero value? Suppose this value as 1. Okay. What should this vector be? So this is also 0 vector. Okay, 1 times this vector should be 0 vector. In that case, this guy should be 0 vector. So if the very first vector is 0 vector, and then it means this vector, even though we have only one vector, that is linearly dependent set. Okay. Okay, so considering the first vector is really simple, because we only need to check whether this vector is exactly 0 vector or not. Okay, if it is non-zero vector, then this first vector is linearly independent. By only considering only one vector, and then we gradually increase the vectors that we consider. So we add one more vector, which is our second vector, and then even though we have 100 vector, we only consider the first two. And then we determine whether, or we check whether these two vectors are linearly independent or dependent. Okay, so we learned about it. So if the second vector is not inside of this line, okay, in that case, those two vectors are linearly independent. Okay, okay, and then we now add one more vector. So we have 3 vectors. Okay, and then 3 vectors. So you do the row reduction only using the 3 vector, and then they are linearly independent. And then we can gradually increase one vector at a time. Okay, and then let's assume that suppose at maybe 10 vectors. Okay, at the time of adding the 10th vector, we first found that those 10 vectors are linearly dependent. In that case, these 100 vectors are automatically linearly dependent. Okay, then let's think about why. And So up to 3 vectors, suppose we couldn't find any kind of linear dependence relationships, which means by using only 3, those values will become 0, right? So this is the only solution. And then when adding the fourth vector, we finally found that some non-zero relationships. Okay, and in that case, this guy will be non-zero value, right? If this is a 0, and then still they are linearly dependent, and then we should be able to find some non-zero values in the first 3. But we assume that using only the 3, we couldn't find it. So if if we found a linear dependence relationship at the time when we add the fourth vector, and then it means the corresponding coefficient will be non-zero value. Okay? In that case, this guy is, suppose this value is 1, and then this value might be some other values, and then from here, we do the same thing of moving this guy to the right, and then represent the fourth vector as linear combination of the first 3. Okay, and then this one, here the point is, if you can find this linear dependence relationship only using 4 vectors, and then you can automatically say that 100 vectors are already linearly dependent. And why? So suppose these values was something like -1, 2, 0, and 1. So this was one linear dependence relationship. And then how can we change it, or how can we utilize this fact to create linear dependence relationship on 100 different vectors? So in the case of 100 different vectors, v1 through v4, and we have to have a v5 and v100 equals 0. Right, and the remaining values can be set as, so it's a quite trivial manipulation, but we have to still find at least one non-trivial solution satisfying this in order to be able to say that 100 different vectors are linearly dependent by using the fact that the first 4 are linearly dependent. And then how can we create from this solution into this equation? So I'm gonna just set it as -1, 2, 0, and 1, and the remaining coefficient from v5 through v100 as 0. But in this case, it is still a non-trivial solution when considering all the 100 vectors. Okay? So again, in practice, suppose you are given 100 different vectors, and you want to find out whether they are linearly independent or dependent. And the practical method to efficiently find the answer for it is you just gradually one vector at a time, and then try to do the row reduction. And then let's see if in the middle of this process, see if you can find some linear dependent relationship. And then if you're lucky, and even if you are given like 100 or 1,000 vectors, if you can find maybe a linear dependence relationship using only 4 or 10, and then that's when you can just stop, okay? And then obtain the solution, or obtain the conclusion that 100 different vectors are linearly dependent. And then this process is exactly the same as like adding one vector at a time, just like this. So I give you this vector and this vector, and then the third vector, and see if this vector is represented as a linear combination of the previous vector, okay, and so on. So this is kind of a sequential, kind of the way of an understanding this linear dependence relationship as a kind of sequential addition of these vectors, one vectors at a time. Okay, so that's it for today. And, yeah, please submit your homework by next Monday, and then yeah, let's meet next Tuesday. Thanks. You mean uploading this picture? So I'm uploading the class videos, and then you can find it there.
I found the program that can run alongside with Octave. I will show you.
한국어로 해도 돼요.
터브처럼 요즘 프로그램 하나 또 찾아가지고 어디 또 까느라고
네.
저 과제 제출 그거 채점이 어떻게 되나요?
아, 채점 기준이요?
네.
아, 왜요? 뭐 점수가 좀 깎였어요?
나름 열심히 했는데 92점 나왔는데.
아, 그래요? 그거 이메일로 좀 물어볼래요. 이메일로 좀 다시 보내줄래요?
아, 네.
그러면 어디서 뭐 감점이 됐는지나 이런 것들을 시험지나 뭐 이런 데서 좀 확인해보고 좀 알려주세요.
아까 이렇게 벡터가 했을 때는 리니얼리 인디펜던트
아,
뭐에 따라
하나일 때는요, 걔가 0벡터면 리니얼리 디펜던트고 0벡터가 아니면 리니얼리 디펜던트.
스칼라가 0이면
벡터가 0이면. 네.
벡터가 0이면
네. 벡터가 0이면. 여기 있습니다. 네. 그러니까 결국 정의를 따져보면 어떤 벡터가 주어졌어요. 그래서 걔에 대한 리니어 컨비네이션을 생각을 할 때 그 리니어 컨비네이션이 0인 호모지니어스 리니어 시스템을 생각을 하는 거예요. 그랬을 때 non-trivial solution, 그러니까 trivial solution은 이 코에피션트를 무조건 0으로 세팅한 게 trivial solution이었고, non-trivial solution을 찾을 수 있다면 linearly dependent 한 거예요.
이때는 리니얼리 디펜던트
네, 네, 그렇죠. 그러니까 즉 그러면 여기에 non-zero가 들어갈 땐 그때는 과연 이 벡터는 뭐가 돼야 되냐?
인디펜던트가 되는 거예요?
자, 여기가 linearly dependent 하다라고 생각을 해봐요. 하나짜리가. 그러면 여기가 어떤 난제로 값으로 채워졌을 때 이게 만족이 돼야 되는 거죠.
네.
그럼 그 난제로 값을 예를 들면 1이라 그래봐요.
0벡터가 돼요.
네, 무조건 얘네들은 다 0이 돼요.
그러니까 리니얼리 인디펜던트가 됩니다.
linearly 그러니까 벡터가 0인 거랑 리니어 컨비네이션 그 가중치가 0인 거랑 지금 다른 거예요. 그러니까 요게 가중치고요. 요게 주어진 벡터예요. 요 주어진 벡터가 어떨 때, 그러니까 linearly dependent의 정의는 요 가중치를 어떤 값은 최소한 하나는 난제로 설정할 수 있어야 linearly dependent. 네.
아까 뭘 그려줬지? 먼저
제가 오늘 출석 안 부르고
네, 안 받았어요.
요건 주피터라는 프로그램인데
네.
아이파이썬 혹시 프로젝트 버전 내는데 그거 후속 버전이에요.
네, 뭐 알아요.
근데 여기서 옥타브 크면 누가 만들어 놓은 게 있어가지고
그래요?
옥타브가 깔려 있으면 그걸로 연동해가지고 쓰는 거예요. 여기서 이제 그래피컬이라서
네.
레이텍 수식 출력도 되고 마크다운으로 문서 형태로 작성해서 이걸 엑스포트하는 것도 돼요. 빨리 돼요. 편하게 되더라고요.
네.
다운로드 에스 뭐 이런 식으로 해서 PDF도 되네요. 레이텍 변환, 레이텍을 거쳐서 PDF 변환까지 한 방에.
네, 저거는 네. 그러니까 PDF로 익스포트를 하는 거죠. 그러니까 여기서 숙제를 해도 좋아요. 네.
네.
저것도 굉장히 좋은 솔루션일 것 같아요.
그 2차원에서
네.
2차원에서 만약 2차원의 벡터 3개 이상 있을 때는 어떻게 하든 간에 무조건 두 벡터 하나의 벡터가 두 벡터의 그 컨비네이션이니까
네.
무조건 다 디펜던트가
네.
되는 거예요.
맞아요. 그래서 이게 아마 좀 바로 다음 슬라이드들에 나올 텐데 우리가 방정식이 있고 그 다음에 그 베리어블 그러니까 변수의 개수가 있을 때요.
네.
여기가 예를 들어서 3이고
네.
여기가 5다. 그러면 그게 약간 2차원일 때 3개 벡터가 있다라는 말이 이런 매트릭스가 2 by 3이에요. 그죠?
네.
이런 경우는 네. 지금 이야기한 것처럼 무조건 리니얼리 디펜던트 해지고요.
네.
그건 왜 그런가 또 생각을 해보면 결국은 이거 x equal 0로 만들었을 때
네.
이때 솔루션이 0이 아닌 솔루션이 있느냐 난트리비얼 솔루션이 있느냐 즉 그리고 그건 뭘로 결정되느냐 여기서 피벗이 모든 베리어블에 다 피벗이 있느냐로 결정이 되는데 로우는 2개밖에 없고
네.
그러니까 피벗은 2개밖에 우리가 끄집어낼 수가 없어요. 근데 베리어블이 3개가 되면 누군가는 무조건 프리 베리어블이 돼야 된다는 거예요.
네.
그렇게 또 이해를 할 수가 있고 그래서 그걸 일반화시키면 여기 값에 비해서 이 값이 더 많으면 즉 얘네들이 살고 있는 스페이스보다 베리어블의 개수가 혹은 벡터의 개수가 더 많으면 그때는 무조건 리니얼리 디펜던트예요.
아까 여기서
네.
1차 강림의 정의가 나오고
네.
1차 강림의 특성이 나오고 여기 이런 정의 같은 게 나오는데
네.
그러면 아까 말씀하신 것처럼 여기서 만약 V2가 0벡터면
네.
그 00000이 아닌 그러니까 x가 모두 0이 아닌 그런 해를
네.
가질 수 있잖아요.
네.
그러면 자명한 해가 아닌 다른 해를 가지는 거잖아요. 근데 그것도 1차 독립이라고 하셨던 것 같은데
1차 아니요. 자명한 해 그러니까 트리비얼 솔루션이 아닌 거가 하나라도 있으면 그거는 독립이 아닌 거예요. 리니얼리 디펜던트한 거예요.
그럼 만약 V2가 0벡터일 때는 그럼 그 V2를 제외한 걸로 다른 걸로 다 1차 독립이라는 거예요.
V2가 0벡터?
네.
그러니까 여기에 0벡터가 하나 껴있으면
네.
얘를 이제 0이 아닌 애로 만들고 나머지는 다 0으로 만들면 이게 우리의 난트리비얼 솔루션이 되는 거예요. 그죠? 그러니까 얘네들은 그러니까 독립이 아닌 거고요. 디펜던트 한 거고. 네, 그 다음에 얘를 뺐을 때, 얘를 제외했을 때.
근데 여기 이걸로 보면
네.
얘가 0벡터면 어쨌든 서로 스칼라배가 안 되는 서로 스칼라배가
0벡터는 다른 애들의 스칼라배 어떤 벡터들을
그냥
가지고도 스칼라배가 돼요. 왜냐하면 0벡터 이꼴 0 곱하기 뭔가를 하면 0도 스칼라배거든요. 0 곱하기 어떤 벡터를 한 것도 스칼라배라고 우리가 부르는 거예요.
그냥 제일 상위의 개념으로 이 정의를 그냥 사용하고
네.
다른 편의성을 이런 정도 사용하고
네, 맞아요. 네,
그러면 저희가 문제를 풀 때는 여기 나온 것처럼 정의 7번처럼 하면 되는
네, 맞아요. 하나씩 이렇게 해갖고 맞아요. 네.
그리고 하나 더
네.
동차선형계와 비동차선형계가 이제 평행 이동하는 그 해집합
네.
그게 만약 동차선형계에서 해집합이 3차원 공간꼴을 나타내면
네.
4차원상에서 평행한 3차원 공간이
네. 맞아요. 네. 3차원이라는 공간이 이렇게 그게 중요한 건 원점을 지나는 공간이었는데 4차원에서 근데 그게 이제 어떤 그러니까 0이 아닌 원점이 아닌 어떤 지나는 점으로 이렇게 평행 이동을 하는 거예요.
책에는 그림으로 못 그려서 그게 설명.
그렇죠. 4차원 이상은 우리가 못 보니까. 네, 수고했어요.